international undergraduate program of statistics called the IUP of Statistics for Indonesian and international students, where English as the intermediate language in learning.
Random. So it means that sample random has two.
While studying, the IUP students will get international exposure such as students exchange, international internships, international short-term academic, have an opportunity for double degree in ITS and abroad university, only 4 years. Also, get national and international certification. In IUP of Statistics, the students educated by competent lecturers, also supported by complete facility. There are 5 statistics laboratories, includes Laboratory of Computational Statistics and Data Science, Laboratory of Business and Industrial Statistics, Laboratory of Social Statistics and Population Studies, Laboratory of Health and Environmental Statistics, and Laboratory of Economics and Financial Data Analytics. Representative Classroom, Statistic Corner, Cool Sigma Garden, Musola, and toilet. Besides academic support, the students also supported to develop themselves through students' organization and sports activity.
Hi all, my name is Adina Rama. I'm from Statistics IUP Batch 2020. I would like to share a little bit of my experience of studying abroad to Canada under Canada Agency Scholarship and UMAP Special Scholarship. Along the semester, I definitely feel a couple of hard times, and I am very thankful for International Office from ITS. They really guided me and were very helpful. They made my experience even more amazing. I definitely made a couple of friends there that I wouldn't have made if I stayed in Indonesia. Lastly, I hope that a little bit of my experience would be one of the reasons for you guys to choose Statistics IUP.
In now era, English is not skill, but necessary even though the requirement. So, join in IUP of Statistics is the best choice for preparing ourselves to compete in global level. International Undergraduate Program of Statistics, ITS.
Hello, good morning all. Welcome to the world-class professor-like international seminar on statistical learnings for spatio-temporal point processes. I am honored to welcome you all participants from all across Nusantara, those who are joining us here on Zoom, and some who are streaming live through YouTube. My name is Sophie Andari, and I will be your moderator today. And with us here, we have the head of Statistics Department at ITS, Dr. Kartika Fitriasari, the Dean of Scientific Faculty at ITS, Professor Hamzah Fansuri, who is joining us online, and of course, our guest speaker from University Jaume I, Spain, Professor Jorge Mateu. Good morning, Bu Kartika, Pak Hamzah, and Professor Mateu. Again, it is a great pleasure to welcome you all participants to this seminar from Surabaya, from the Department of Statistics, Scientific Faculty Institute Technology 10 November. This seminar is a part of world-class professor-like program granted to one of our associate professor, Dr. Ahmad Khairuddin. Before we begin, I'd like to mention several things. I'd like to remind every participant who is here on Zoom to kindly mute your microphone. However, feel free to use our seminar virtual background. You may find the image posted on the chat box right now. There will be a specific website link you can use to record your attendance. That particular link will be available later on the chat box on Zoom and also on YouTube. So kindly wait for the link, and we will post it during the seminar. This event shortly will be started with the opening speech from the Dean of Scientific Faculty at ITS, Professor Hamzah Fansuri. Next, we will have a quick snapshot to commemorate all of us for being here today. Afterwards, we will listen to Professor Matthew's talk, followed by a Q&A session. All right. Before we get to the talk, we will be listening to a welcoming speech from the Dean of Scientific Faculty at ITS, Professor Hamzah Fansuri. Please, Professor Hamzah, the screen is yours.
Thank you, Sophie. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Good morning, and also warm welcome for Professor Jorge Matthew. Yeah, we met last year in the World Class Professor programs in Surabaya, and we welcome you again here in ITS. Although at the moment we are in online seminar. As representative of ITS, I'm very welcome Professor Jorge, and thank you very much for becoming our guest, World Class Professor this year. And also, I thank Professor Jorge because you also one of our adjunct professor in ITS, and for statistics departments who organized this very excellent World Class programs this year. Also, thanks very much. And this World Class Professor is part of what the head of department, Dr. Kartika, mentions in the video, opening video. The statistics department is heading to international institutions who provides education and research and also service in the statistics. There are 6 laboratories, 6 research focus that has been mentioned before in the video, and also statistics department is the fastest growing department, become leaders in many areas in teaching, research, and also public service. This part of activities, World Class Professors is a continuous effort of ITS and a whole. Of course, this is in statistics departments to always do the improvements in many ways. Yeah, and especially with Professor Jorge, this activities is to improve the collaborations and also many other things that we can do together in order to get into the vision of statistics departments. I'm very much welcome to all the activities like these ones, and I would say it is not only stop at world-class professor. I'm hoping that this will broadening our collaborations, will increase what's the service that can be given by statistics department and also ITS to all our students and society, and also, of course, in the development of the science. Yeah, in this case is statistics. I welcome all the attendance as well this morning. So there are 113 participants, including me and Professor Jorge. And I'm hoping that this webinar this morning and also other activities following the World Class Professor programs will provide excellence and also improve our knowledge and also information regarding the topic that will be given by Professor Jorge. Please take all the necessary thing for all of you, to improve your knowledge and also the information. And also don't forget that Professor Jorge is our adjunct professor. That um, Professor Jorge is part of our department, statistics department, also ITS. And please enjoy this webinar. And have this webinar will run very well until the end this afternoon. That's all for speech from me. And as Dr. Sophie mentioned that I'm also asked to officially open this webinar, and then with Bismillahirrahmanirrahim, I'm officially open this webinar. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you, Professor Hamzah. It would be great if you could stay, Prof. But I heard, I heard you need to attend other meetings this morning.
No.
Okay.
Yeah, I cancel my meetings.
Wow, it's an honor. Thank you. Thank you again, Professor Hamzah.
Yeah, you're welcome.
And once again, I'd like to remind Bapak Ibu participants on Zoom to kindly mute your microphone, but feel free to use our seminar virtual background. You might find the image posted on the chat box. And also there will be a link for you to record your attendance. That particular link will be available later on the chat box during the seminar, chat box on Zoom and YouTube as well. So kindly wait for the link. All right, I'm back. Now I'd like to invite everyone on Zoom to turn your camera on, and we will have a brief photo session. Let's see. Yeah, nice. And it's great to see everyone's face on screen. Please hold your best smile or grin or thumb up, and we are going to snap a quick screenshot for every page. How many pages do we have? It's 3. Okay, cool. Now, here we go. Page 1. 1, 2, 3. Awesome. Let's move on to page 2. Please hold your smile. And here we go. 1, 2, 3. All good? Should we move on to the last page? Page 3. Yes, 1, 2, 3. Done. Great. Thank you all. You can stay on camera, or if you want to be off camera, that's also fine. Now, it's time for the main event, the talk about statistical learnings on spatio-temporal point processes by Professor Jorge Mathieu from University Jaume I, Spain. It's a great honor to welcome him for the second time here in Surabaya. I am going to read his profile briefly. He is a full professor of statistics at the Department of Mathematics of School of Technology and Experimental Sciences, University Jaume I in Spain. He obtained his bachelor's degree in math and stats in 1992. His master's was also in math in 1995, and his doctoral degree in math in 1998 from University of Valencia in Spain. In 2013, he was awarded as the Best Associate editor of Journal of Agricultural, Biological, and Environmental Statistics. Last year in 2022, he was awarded as the editor-in-chief and associate editor of 12 top journals. In the same year, he was awarded as one of the top 8 amongst the Spanish researchers in statistics and probability. Yeah, he was involved in more than hundreds of scientific publications and has written more than 20 books or book chapters. Currently, his Scopus Age Index is 28. Well, I could go on for hours reading his tremendous achievements. So you may want to check out his profile on his website. The link is available on the chat box. I think it is available now. So, Bapak Ibu participants, for any questions that you might be thinking of while listening to the talk, you can drop in those questions on Zoom or YouTube chat box. Later, we will curate the questions to be addressed during the Q&A session. So, finally, Professor Matthew, the screen is all yours.
Yes. You can do the slideshow. That one.
Yeah, so can you hear me? Yes. So thank you very much for this very nice presentation to all of you, starting from the Dean and to the, let's say, the main speaker today. It's not me, it's you who is conducting this seminar. And thanks, Ahmed, for inviting me again, and the department for having the let's say, the second chance of being here. It's a pleasure. I mean, when I've from the Dean, I've listened that I'm member and part of this department is like a pleasure. It's like a pleasure for me. So I'm really happy to be here again. And the idea of this seminar is just to, let's say, to bring a new topic that is clearly emerging in spatial statistics. When talking with Ahmed to prepare this seminar, I provided him like 2 big topics, and he immediately answered me saying, no, let's go to statistical learning, because this is something that it's really new, and it's something that it's becoming a trend topic within computational science and the spatial statistics. And this is the reason why I am here today and talking a little bit about this statistical learning for spatial temporal point processes. This is joint work. I mean, this is something I'm kind of new in this topic because I'm coming more from the spatial temporal point process point of view. But clearly, we need to, I mean, after some years learning about these statistical learning processes, which is something like it has to do with more computational based things, it came to my mind that clearly we need to join these 2 big areas. One area is spatial statistics itself from the statistical point of view, and the other area is statistical learning or machine learning or deep learning, as you want to call it, which comes a little bit more from the computational point of view. And joining together brings good things to both areas, to both sides of the same story. And this is the idea of this seminar, to put this together and to motivate people, those that are wanted to enter this big thing of statistical learning and spatial statistics. The idea is to motivate them to start with this thing. Well, this seminar is based on several papers that, as you see, they are kind of really new papers. All these papers, these 4 papers are coming from 2023. So in fact, they have not been published. So they have been accepted, they have the DOI, but they have not been published so far. So it means that this is clearly a very new thing, right? And I will be talking about basically the first three, because I don't have time just to talk about the fourth one, probably in my next visit. But the thing is that the first three, you see, the first one is being published in Advances in Data Analysis and Classification, and this is one of the main things I will be talking about here today. The second one is published in Journal of the Royal Statistical Society, C. Again, it has something to do with point processors and neural network modeling. And the third one, which is the last one I will be talking about, is a joint paper with George Muller, and it's published in STAT. And you will see that So let's start with something that probably you know, and probably as you were a student, you were confronted with this type of data. This is a classical data. It has nothing to do with point processors, but this is a way to motivate what we will be doing later today. This is the classical Fisher type of data where we have three different observations from random variables. Now, what we observe is point patterns, spatial or spatiotemporal point patterns. So we change the type of observation, but we are not changing the aim or the goal of our problem. The goal is the same. The only thing is that we start from something different. We start from something which is called spatiotemporal point patterns. So this is the data, the observations. Our observations are given by a number of data. For example, in this case is X, and you see the subscript there is based on two elements. One is S, the other one is T. S is the species, so the group that particular observation belongs to, and T is the temporal, the repetition or the temporal moment for which I'm taking a sample, right? So basically, what we have is this sort of thing, like observations, which are, let's say, numbered with the temporal instant, which I'm taking that sample, and the group that that observation belongs to, right? So if we take this into the previous example, clearly T is something going from 1 to capital T, which is 50. Because remember that we had in the previous example like three different temporal, let's say, repetitions. So capital T is 50. Then we had three different groups to classify to. This was M. So SI belongs to 1 to M, and N is 3. And we have capital N equals to 150, which means that we have this number of observations. And the question is new arrivals X star, which we know all the data except that the group, and we have to classify this data, right? So this is exactly the same kind of thing, like this one, except that now we put a little bit more of more of formality. So we put a kind of letters and numbers describing the whole data set. But as I say, now we change our data. The type of data is what we have in front of us right now. Now we have point parents. These collections of points, of observations in a particular window, right? And we have a species. All this you can have here is, you see on the first row, we have a species called Acaldi, and that has been measured, has been sampled in different temporal instants, in 83, 85, 90, etc. We have another species, which is Cat. Again, it's been sampled in different temporal instants, and so on. So this is the type of data we have right now. You see, we have changed from classical random variables, as in the iris example, to point parents in space. So in this particular data, by the way, this data, BCI data, is a kind of famous data that has been used in many, many applications because it's a huge data set that provides information on a species, on spatial point parents, and on repetitions in time. So it provides lots of information, and it's useful in many, many applications. So what we have here is 130 most abundant species. So small m is 130, is the number of species that we will be working with. You see, it's a huge quantity of groups or species, right? Then we have up to 8 temporal dependent repetitions. Remember, from 83 to 2015. Then we have a number of point parents. The spatial point parent we have is 1,040, which provides 1,800,000 something alive trees, right? So this is our data set. And the problem, a classification problem or a discriminant problem. We need to know, or we need to build a context, a framework, where if a new, let's say, a sample of trees, so a new spatial point pattern arrives, and we don't know to which species it belongs to, we should be able to classify correctly this new arrival. That is the idea. So we need a little bit of formality. We need a little bit of to know what we will be working with. So our window will be denoted by W, capital W. X is our spatial point parent. Locations, particular locations, individuals in the point parent are called UV with this type of letters. And then we have 2 letters. One is sky, which is the space of all spatial point parents, and one is capital X. One thing is the space, so let's call the abstract space of all point parents, and another one is capital X, which is a particular spatial point process that generated our spatial locations, right? So this capital X is, as it is defined as a spatial point process, is a function, it's an application that goes from a probability space down to the space of all point parents, with the corresponding, let's say, a structure of a probability space. We have a sim algebra, we have a probability, and we have the probability generated by this spatial point process, right? Fine. And then we have some particular characteristics of our spatial point process. We have rho, which is intensity function, will be the intensity function. We have the paired correlation. We have distance-based functions like the F, G, or J functions. This is classical. I mean, this is not new. This is really well known in spatial point process theory, but we need to put a little bit of context, because all these sort of, let's say, functions and elements will be appearing during the seminar. Fine. So now, if our problem is discrimination, we need a function able to discriminate, right? And this is called a dissimilarity function. And what it does, a dissimilarity function, what it does is a function that has as an arguments 2 point parents, right? So that capital D acting on these 2 point parents provides a value in R. And this value should be very small if the 2 point parents are kind of equal, or could be, let's say, not the same, but very equal, close together, and should have a large value if the 2 point patterns that are being evaluated by D are kind of far from each other, right? This is a simple thing. So capital D as the similarity function provides this sort of information. If they are close together, that's fine. That will be a very low number. If the 2 point patterns are kind of very distinct, then this function D will provide a large value. This is also very general. Fine. But D should also have some kind of two, let's say, properties, which is it should provide information on how two, let's say, point patterns are close enough within a particular group. When 2 point patterns belong to the same group, then these should provide, let's say, a very small value because they are close enough. But also, there should be some kind of, let's say, variation, what is called a stochastic variation, because any 2 point patterns are the same, even if they belong to the same group. So we do not expect that 2 point patterns belonging to the same group should have the same value in D. This is not possible. There are stochastic variations. So these variations should also be taken into account, right? This has to be, let's say, kept in mind when considering the value of these. And then there is another thing, which is very important. In terms of comparing patterns, we have to distinguish between pattern matching or process matching, which is different. Because the pattern is what we observe. So a realization of a process, right? So one thing is saying that two realizations, two patterns are close together, they behave similarly. And another thing is saying that the underlying point processes, those that are providing these realizations are, let's say, close enough. So this is the way we distinguish, this is why we distinguish pattern matching versus process matching. And they are different things. You will see that it's very different to work with patterns or working with the underlying processes. And for example, just assume these two well-known, let's say, point patterns. One is red oaks, it's a species, a type of, let's say, of forest, of trees in the forest, and white oaks, right? So these are realizations. These are point patterns themselves. And you're going to say, oh, how much they are different or how much they are kind of equal or close to being equal, right? So one possibility, and this is in the literature in 2016, is saying, fine, one possibility is defining this D. V of X prime of the 2 point patterns is given by this equation here. This equation is just considering the number of points in small grids. So basically we are counting, we are dividing our data, our point pattern into small cells and counting how many, let's say, trees or events are lying in each one of the cells. And this is this N that appears in the formula. And by this equation here, for D, these authors in 2016, they provided a particular function of D, a particular function of the similarity between 2 point patterns. But again, this is point pattern, let's say, matching, right? So we are trying to obtain a dissimilarity or similarity function based on what we observe, only on observations, so on point patterns. Yeah, in 2017, something similar. The authors did something similar. They changed a little bit this similarity function. You see, it's based more on distances, so rather than counting. The previous one was more on counting on cells. This one is more on distances between events. And we obtain this, again, this function for D. But again, this function D is a way to obtain similarities between two observed point patterns. So this is called point pattern matching, right? We are not caring anything about the process that generates these patterns. We're just observing patterns and we compare 2 point patterns, nothing else. At least this is what they do in 2016 and 2017. But we're going to do something different, right? Because, as I say, one thing is, let's talk about random variables, not point patterns at the moment. One thing is saying that two realizations of two random variables are close together. Another thing is saying that the random variables themselves, with all their nature, stochastic nature, are close enough. Right? This is a different question between these two. So now what we are saying is, rather than comparing point patterns realizations, we would like to see how much the generators, which means the point processors themselves, are or not equal. Right? So when we say that 2 point processors are equal, or at least are kind of statistically indistinguishable, well, they can be in terms of their probability distribution. If the two probabilities of x and x prime are the same, they are not distinguishable, then we can say that the 2 point processors are kind of equal, right? Fine. So this is what we are right now interested in, right? In equality, statistical equality of the underlying point processes. Yes, this is fine, but how can we find out this? Because now it's a little bit more difficult. Now we are not working on the realizations themselves. We're working on the stochastic processes, right? So one possibility is saying, fine, let's try to define what is called this capital G function. This G function is a function that goes from our space of point processes down to something which is called a feature space. The features. And the features is something that is very closely related to the probability distribution of the underlying process. So in a sense, we are saying that I want to extract the hidden features of my point process, right? How can they do that? Fine. This is the very final, let's say in the bottom line here, this is a way to define this. Now our capital D function, our dissimilarity function, rather than acting on x and x prime, so on the point patterns, it's acting on g of x and g of x prime. So we apply g over each one of the point patterns. We now go into the feature space and we calculate d over in the feature space. We translate our problem from the space of point process, which is a kind of abstract thing, down to a space of features. Now we will be talking about what is a feature. But the idea is this translation, fine. And then what is D in this new feature space? D could be, for example, a particular distance, you see distance on F, between these G functions, right? And you will see we have lots of possible distances and lots of possible G functions. You will see right now. For example, and this is something that people working on point processes, they are aware of this, because the idea is that if we go to the literature and we provide, we look for kind of common summary statistics, we will notice that many common summary statistics, they have this form here on the first line. This, you see, this G of X is the sum over all individuals of particular functions H of these locations, right? For example, if this is too general, let's go to a more particular case, which is the first order intensity function. The one you have here with rho hat is a classical simple intensive first order intensity function. And you see, this is just the sum over all individual events of my point pattern of a kernel function, which is kind of a density function, divided by something which is called a normalizing constant, the integral of this. Well, this integral, this kind of normalizing constant is a way to obtain an unbiased estimator of the intensity, right? In any case, you see that this rho is a very particular case of what we have in the very general case up there, which is the G function. And just notice this, and looking at the bottom images. On the left-hand side, the original point pattern. We have locations, events in our window. This is X. Now we transform X with G using rho. And then we go from locations to an image. This image is the first order intensity function. It's an estimation of the first order intensity function, right? And so now what we've done here is going from the space of point processes X down through G, or in this case through rho, to, in this case, the space of feature. This can be considered a feature of our point pattern. The only thing is that we have to be a little bit careful with this, because you see the difference between the central image and the right image. In the right image, it seems that there is almost nothing. Well, there is something there, but it's difficult to see. But because this rho, it depends on a kernel. The kernel depends on a bandwidth parameter. And this is very, that's selecting the bandwidth parameter is something crucial, is something important in our kernel function. If we do that in the let's say in the wrong way, we can get something like a rho equal to the right-hand side image. It means nothing, right? So during this process, we have to take care of some parameters appearing in the process of the estimation of rho. But in any case, assuming that we are able to do the right thing, this is a clear example of how to go from the original point pattern locations to a feature image, in this case, the first order intensity. But we have more possibilities. Rather than the intensity, we can use what is called second order summary statistics. For example, we can use the K function, we can use the pair correlation function. You see the difference between the two in their estimation. The difference is that the K function is a kind of increasing function. So it's a type of distribution function. Yes, a cumulative distribution function. And this is compared with the pair correlation, the second line here, which rather than using the indicator function, which aggregates, it uses a kernel function, a kind of density. In fact, the two of them provide the same type of information. One is kind of associated to a distribution function. The other one, the pair correlation, is associated to what would be a density function, right? But these are two very well-known summary statistics. And again, we could be using these two as a feature, as a going from the original point pattern into something which is called the feature point, the feature space, through the capital G function. And in this case, you see in the bottom line, let's say the output of this. From the original point pattern on the left-hand side, we go to the K function, which is a simple function depending on distances, and then we have the value of the K, or the corresponding pair correlation function. Again, depending on distances, we have the corresponding value. So you see very different things. Before, we went from locations to images to define our feature space. Now we go from locations to functions to define our feature space. You see? But we can do even more things. I mean, we can have some other called distance-based functions, and we have this capital F function, we have the capital G function, we have the capital J function. Again, these are very well known in the literature of point patterns, and these are functions that provide information on the spatial structure of our point pattern. Because depending on the behavior, we know a little bit if the events are basically, let's say, randomly distributed, or they have some kind of aggregation or some kind of regularity, right? In any case, we could be using also these functions as a capital G function, which is transforming locations into features. Fine. But then we have a problem. As always, in doing research, it seems that everything is fine, that you arrive to the end, and then, oh, something happens. What happens here? Which one we should be choosing? I mean, there are lots of them, and this is just a sample of them. I mean, I've mentioned 6 of them, as you have here, from raw down to the J function, but there are lots of them. So if someone comes and asks us as our researchers, please, which one provides better results? We don't know. And why we don't know? Because if we're using, for example, in the capital D, we're using rho. Rho, remember, is the first order intensity function. We can use the classical L2 norm, right? Which is the integral of the square difference between these two. Well, this could be a useful thing. That's fine. Or you can say no. Rather than rho, I'm using k, and then I'm considering again in this case the norm, the infinite norm, which is the supremum norm of the difference of the two k's, right? And again, we have something there. If you go to this paper 2015 in Biometrical Journal, you will see that we have lots of, let's say, problems in terms of classification. Remember that we are heading to a classification problem. So we are having lots of problems when we are using any of these functions. Why? Because of the stochasticity of our, let's say, patterns, and then the corresponding estimators. Because you could have 2 point patterns that are very close together. I mean, they could come from the same process and being quite different in terms of realizations. And when you use rho, when you use the k function, or when you use whatever type of function, you get, let's say, not wrong, but not good results. Yes, and we have a very clear example I can tell you, and people from point process literature know, which is you have 2 different types of processes. If you've ever heard about, let's say, Hawkes point processes and log Gaussian Cox processes, so you have 2 generating different types of stochastic processes. If you compare realizations of the 2 through the k function, they are the same. The k function is basically the same type of function for realizations of 2 different processes. Because we cannot distinguish realizations, even if they come from different stochastic processes, right? So what the message so far is that it's really nice going from point patterns into feature spaces. Perfect. The second message is it's very nice defining the capital D function as a similarity function. That's fine. And it's very nice going to X, which is the original location, to something which is a transformed feature space through some of these summary statistics. But at the end, we have a problem there because they are not completely useful. Then we need something extra. We need something more. And what is something more? And this is the idea and the motivation of this seminar. Something more could come from these computational deep learning approaches. Let's provide a framework that rather than using a particular summary statistic, let's try the deep learning framework to provide the best option for transforming from X to the feature space. That is the idea. So the second part of the seminar is in this way. Let's forget about summary statistics. They are useful. I'm not saying that they're not useful, but not for this particular problem. And let's try to use an alternative approach. So now we have our point pattern. It's here on our screen. First idea. Well, here we have U1, UN. The U are the events, all these small dots in the window. And then the first thing is, that's fine. Let's partition our window into small cells, Bij, from I1 to D1 and J1 to D2. So we have D1 times D2 cells that are completely covering our window W. Fine. This is our thing, first thing. Second thing, this is our cells now. Now we're counting. Now we count how many U's, how many locations are lying in each one of these Bij. And you see, this is exactly the same as this. The only thing is that we have superimposed a grid and we have discounting numbers on this grid, right? So you see, we've gone, now we have what is called discretize the point pattern, right? And just to give you an idea, the original point pattern is called X, just X. The discretized point pattern is called X bar, right? So every time you see a bar on top of X, that's indicating the, let's say, the number of points in each one of these Bij cells. This is a way to distinguish between the two. Fine, we're just at the beginning. This is the very first operation. Second thing, we need to do something there. Why not providing convolutions between our X bar, which means our counting of data, of locations, and some particular, let's call filters or kernels, right? So now we need to, let's say, to provide capital F. And capital F, you will see it's just a matrix, Fij, that goes from D1 times D2, but super 1. So the difference between one thing is D1, D2, which is the dimension of the original point pattern. And another thing is when we have the superscript 1 or 2 or whatever, when we have a superscript, that's the dimension of the filter. If you don't know, if filter for you is kind of abstract thing, think of a kernel or a matrix with that dimension that is being convoluted with X. The convolution is given by this equation here. This is something known. So X bar convoluted with our filter F is just the sum of each element of X times each element of F. Right? The only thing is that we have to take care a little bit about what is called valid padding or zero padding, because remember that for the valid padding means that the indexes, they have to be in the right order. We cannot go outside the correct indices of our X. But this is something, a particular thing. This is not. It's important, but it's not important. Is the important message here. The important message here, and you will see right now some particular example, is this thing that. From the point pattern, we go to the, let's say, the point pattern discretized by the number of cells, and then we have a convolution of this together with some filters. And we get something like this. And this is very simple to, let's say, to explain and to understand. On the left-hand side, we have the discretized point pattern. In this case, we have 8 times 16. You see, we have 8 rows and we have 16 columns. Yes, and numbers are number of events of the original point pattern into this window. Fine. Now we have on the right-hand side the kernel, the let's say the filter, capital F. And this kernel, in this particular example, we have chosen a 3 times 3 kernel with particular values. These ones here, and the convolution of the two is given in the second row plot. Is just the product, as I say, from one matrix times the other, and we get this 6 times 14 matrix. So we have transformed the original point pattern, 8 times 16, into something which is a little bit smaller, which is 6 times 14, through this filter, through this kernel, right? We can do this. This is another example, but this example is just to see that if we change the kernel, you see the kernel here is -1, -1, -1, and then in the next example is 0, -1, 0, right? So the message is, if we use a different filter, we have a different output. That's for sure, right? The dimensions are the same, but with different figures, different numbers, because the kernel, it's been a different one. Fine. This is again another example, and I would like to bring you to your attention. And again, we have the original discretized parent, we have a kernel, in this case 3 times 6, and we end up with a 6 times 11, let's say, output of that thing. So there are two messages out of this. First message, the output depends very much on the kernel used, on the filter used. Second message, the kernel has no particular restriction of being a square matrix. It could be clearly, as in this case, non-square. Fine. Yeah, and this is different examples. Now, why this convolution is important? This is at the basis of what will be called a neural network, right? So let's go now deeper into what is a neural network. Now, people that are attending this online and that they have worked a little bit on neural networks or in general machine learning, they will understand this sort of thing, because this is not new. I mean, I should say that we're just using something which is known in this more computational, let's say, based branch, but we have, let's say, changed a little bit or adapted to our particular case of point patterns. Now, our X time F, because you can say, yes, we've seen that F is very important, the filter is very important, fine. What is the filter for us? You see, this convolution could be interpreted as the sum of these capital A, let's say, values, right? The sum is going for all u's, so for all individual events of our point pattern. And this capital A, what it is doing is just something simple, which is the indicator of U belonging to a particular cell. So we say, okay, we go to U. U is one particular location in our window. If this location belongs to that cell B, fine, this is 1. If it's not in B, it's 0. If it's 0, it is not counting. If it's in B, it's 1, and then it's 1 times my filter. This is everything we are doing here. And this is very close to the first order intensity function that we were using before, to the rho that has appeared before, right? Fine, this is A. The sum of A's provides the convolution of X with the filter. And then what is our feature map? The feature map, and this is substituting our capital G function, right? Now the feature map is the convolution, and we add what is called a bias term, and then we have, so just to give you an idea of the process to obtain capital H, we have the data, the point pattern. From point pattern, we go to the discretized point pattern. From the discretized, we go to the convolution of the discretized X bar with the filter. Then we add some biases. Biases are parameters to be estimated. They are not known, right? And then we apply something which is called an activation function. The activation functions are, let's say, they are in the hidden layer. Hidden layer means that we are not observing them, but they are functions that go through one particular input, and with a nonlinear function, they provide a particular output. Yes? So with this F1, we obtain capital H1. And capital H is just what we call a first layer of feature maps. So it's called a first layer of metrics, and it provides information on the features of the point pattern. Right? Good. Now you can see, or you can ask, what is this K? There is a K up there at all moments in this slide. There is 1, K, or just a K. 1 means the first layer. The first layer. This is like the first thing we are doing, right? But K is number of kernels, number of filters. And why? You've seen that this is very sensitive to the type of filter that you have used. Fine. Do not use 1. Use K of them. Use 1 type, a second type, a third type, or whatever number of types, K types, and this K is the K that appears here. Yes? So the thing is that this capital H, which is a feature, contains all these transformations coming from F1, from the activation function, and it contains for all cases of kernels used or filters used. How many? L1. Right? Fine. And this is an example, again, from discretized point pattern with a convolution of the kernel, we go to the convoluted point pattern. And then we add 5. 5 is a bias. These B's that have appeared here, the bias or intercept terms, bias. And then, let's say on the second row, when we say convolution plus bias, we applied an activation function. This activation function is ReLU. Well, ReLU is just the maximum between the 0 and the value. So it transforms the negatives to 0 and the positives stays the same. The positives stay the same, right? So basically, this ReLU is kind of an activation. And this feature map, the one we have bottom right, is just the very first feature obtained from our original discretized point pattern. And we have this, and we are in the first layer. Fine. Well, why this work? This is a little bit more of a notational thing. There is a link. There is a link. I mean, this is not by, let's say, by chance. There is a link between the H matrices. Remember that the H is this one here, is the output from the activation of the bias plus the convolution. This H has an intuitive interpretation from the density of the point pattern. So we can evaluate the probability that the H being less than whatever value of Z in terms of f of x, which is the density function of the original point pattern, which is great. In a sense, we provide a probabilistic counterpart of, let's say, our H metrics, of our feature metrics, right? So we are not in the wrong way, in the sense that what we are doing from a, let's say, from a neural network perspective is very much connected with the distribution, with the probability distribution of our point pattern. So that's fine. And we can do even more, something more, which is, you've seen that there are lots of things happening in the process. For example, the filter is not only that it depends very much on the filter values, but it also depends on the dimensions of the filter. Now the question is, which dimension we should be taking? So the answer to this is, fine, to avoid this problem, do pooling. Pooling means that from the original H with particular dimensions, we go down to something which is a summary, let's say, of sub-blocks within this matrix. Because H depends on the dimensions, on the P1 times P2, on the dimensions of the original, let's say, discretized blocks, right? So now we consider these submatrices, and we consider a kind of operation for the submatrices. This is called pooling, and it's a way to avoid the problem of the dependence on the original, let's say, dimensions. So it provides more robust estimations, and in general, it makes us being kind of, quiet in terms of what dimension should be chosen from the very right initial procedure, right? Fine. For example, this is a kind of max pooling. Pooling could be the maximum. So just imagine that the matrix in the central part is the convolution, and then what we say is every 2 by 2 submatrices we consider the maximum of these 4 values, and then we do this max pooling. Clearly, we reduce the dimension from the original down to this in terms of maximum value, but it could be used any other type of, let's say, of operation for the pooling, not only the maximum, the mean, or whatever, right? This is another example that provides the whole thing from the original point pattern down to the pooled feature map. Right. So what happens? Because I said that H had a upper index which was 1K. Why 1? because we can have more than ones. We can have twos, and we can have whatever number of layers, right? So we can repeat the whole procedure a number of times. And then we can build in the same way h at the power of 2, which will be the h from the second layer, and so on. With repeating basically the same kind of thing. The only difference is that before we had the convolution of x in the first layer, because the starting point is 6, we have the convolution of x with f. Now in the second layer, what we are convoluting is f, but not with x, with the output of the first layer, which was h. So you see now that we have the convolution of h times f. And we go into f2, and we could create the second layer and so on with a number of layers, right? There is something which is really known in the community of a neural network, which is what is a perceptron. Yes, a perceptron is this sort of thing. You see, we can substitute the convolution, basically here, the convolution of h coming from the let's say the previous layer with a filter by this thing which is called the perceptron, which is the activation function f that acts on a bias b0 times this sum of weighted, let's say, of weighted operation, which is the sum of weights w's times the h. Basically, the weights are coming from the kernels, right? We are substituting in the previous thing f, capital F, now by weights, by w's, right? This general structure, which is really similar to the previous one, is called a perceptron. And again, it depends very much on number of layers. In this case, we have capital L layer, and it depends on K, which again is the number of, let's say, of types of weights, of kernels previously known, of weights that we'll be using here. But the overall thing is what you have at the end. From the original point parent, through all this network structure, we go down to a feature, let's say a feature map or a feature extraction, which is capital G with all these G, small g, let's say, values, which are the perceptrons. For example, this could be a particular case. I mean, from the original input, which is a message of whatever times whatever, then we say now we use in the first layer, for example, in this case, we're using 4 layers and a final perceptron. In the first layer, we use a 32 by 32. Yes. Then, for example, we use the kernel are the dimensions of the kernel 10 by 20, and then we do the pooling 2 by 2. Then in the second convolution, the second layer, we provide 64, and with different kernel dimensions and pooling and so on. So you see that we need to define all these sort of, let's say, small steps, which we need to define the dimensions of the kernel, the dimensions of the pooling, and finally the number of nodes, which is the number of kernels that we are using in each one of the layers. And of course, the number of layers. This provides at the very end something which is called the perceptron. The perceptron in this case is this function here, this small j function, and this g function, and this will have in this particular case 2048 parameters to be estimated. Yeah, well, this is just wanted to give you an idea of a graphical idea of what we are doing here, in the sense that in general this kind of neural network is being like this, is being built like this. We start from the bottom, from the blue thing. This is what we observe. Then we consider weights, right? The weights are usually linear, and then we have the weights time. In this case, are the x, right? And then we query point parent, which means for the unknown point parent, where I classify that. I will classify that point parent to that index, or to that group for which I obtain the maximum of this probability. So I compare my point parent, the new arrival, with the ones I have from the data set. And I calculate P of these 2 point parents. I classify to that group for which I obtain the maximum P, the maximum probability. That's a logical thing, right? So that is the basic idea. The collection of point parents, the new arrival, and classification. And the classification is based on the probability, and the probability for which I obtain the maximum, the maximum probability of classification will provide the corresponding, let's say, group to which I classify the new arrival. That is the thing, right? Of course, I can obtain my misclassification errors and all these sort of things. But again, P is not known. I mean, it seems that all is done, all is fine. It's fine, except that everything depends on P. And at the moment, we don't know how to obtain P. This is still something to do. Fine, good. Let's go in that direction of obtaining P. Well, this is basically the same kind of thing. So this is repeating the same as previously said in the sense, this is called one-shot classification, which means, or one-shot learning. It means that if my query point parent, the parent which is not known, X star, the way to classify X star into the capital D, which is into some of the existing groups, is based on the fact that I'm obtaining the maximum of Y star using the discriminant model, right? So again, this is in other words doing the same kind of thing. Yeah. So finally, let's go to P, which is the clue here. It's the important thing here. How to obtain, let's say, an estimation of the probability using what is called a CMS neural network, and that is the thing, right? So, and this links to the previous thing. I mean, in the first thing we've done something like how can we use a neural network to obtain features of our point parent, right? That was the first part of the presentation. Fine. Now we say our discrimination or our classification problem depends on P, on a probability, right? How to calculate P? We use something which is called a CMS neural network to obtain an estimator of P. How is this working? Using the perceptron. And how is this? We have the 2 point parents, X and X prime. From X, we go to the feature space of X, G. From X prime, we go to the feature space of X prime, G again. And we have the difference of the 2, right? G of X minus G of X prime. The thetas are the parameters involved in the feature extraction. Fine. Our P is FL plus 1. F, remember, well, I have to go something like 5 or 6 slides before when we call the perceptron. Remember that the perceptron is exactly this expression for P. Is an activation function of a bias plus what was called a convolution of features times weights. Now, in this case, we substitute the weights by betas times the difference of the feature spaces. Right? So this is called the perceptron because it has exactly the same configuration of a perceptron, and all the parameters involved here, which will be the beta 0 and all the beta k's, K1 to K2L, are, again, weights that have to be estimated using the neural network. Well, this activation FL plus 1, it depends on the problem. Note that the output is P, is a probability. As a probability cannot be negative. So we have to select a particular F that provides non-negative values and at most 1, right? So that P is well defined. Because there are lots of activation functions, right? This is just for you to know that we have to select the right F here. That's perfect. As I say, the hyperparameter, there are lots of things. For example, to go to the perceptron, we need the previous activation functions. As in the examples that I've shown you before, the activation functions could be from 1 to L minus 1. Remember that capital L is like the layer L. The activation function is just the maximum. So is the rel function is the maximum between 0 and the value, fine. And then for the last two layers, L and L plus 1, we have the logistic function, just to provide this kind of probability, let's say, value as the output, right? So again, we have to these hyperparameters, they have to do with the number of layers, they have to do with the number of nodes. Remember that the number of filters that we are using or number of weights. We have to deal also with the pooling dimension. All these sort of things that we have chosen in our way, they are called hyperparameters. Yeah, and then it comes, and then what we do with this P, with the probability, that is the probability of our Bernoulli. So how can we estimate the parameters? If we have a Bernoulli, depending on a P that we know, we can calculate the likelihood or the log likelihood, or because we have weights, the composite log likelihood. And then at the bottom of this slide, we have this composite log likelihood that you will see that it has the classical, let's say, shape of a Bernoulli distribution. But there in the input, we have the P's that have been estimated using the CMS neural network approach. You see? So at the end, we have a likelihood-based problem that we have to estimate to obtain the parameters. The only thing is that the input have been, the different input, the P, have been estimated using the neural network rather than a different or classical, let's say, technique. That is the thing, right? Well, I'm going quickly over this because one usual problem we have with neural network is the overfitting. And the overfitting is that, well, it might be the case that we wanted to be so, let's say, so competitive with these models that we added lots and lots of parameters. And then theta was really large, a large number of parameters. Then we have a problem of overfitting. I mean, there is no need. So here we have always this kind of counterbalance between fitting itself and number of parameters, right? So, for example, one way to detect that we have problems of overfitting is that, yeah, our model is perfect in the sense that we have lots of parameters and we have fitted well the data, but in terms of discriminant, in terms of further classification, it goes wrong. So when there is this discrepancy between model fitting, everything seems to be fine, with model output, which is the discriminant, the classification, if we have this thing, it's because we have a problem of overfitting, right? Well, this is one thing. There are like several solutions, two solutions in particular to overfitting, and one is parameter regularization, thing that Ahmed, I'm sure it's an expert in, and that we can control a little bit. I mean, there are some parameters that there no need to be there, and we can control which can be there, which cannot be there, right, by using this penalization term. So this is one possibility to reduce the total number of parameters in the final, let's say, model. No? There is an alternative thing, which is the dropout. But, well, the dropout is also a possibility. It's a kind of thinning, independent thinning. So we're dropping independently some, let's say, a small number of data. When I say data, I mean the original cells or counting in cells. So we are keeping some of them, we are dropping some of them, and we just recalculate the whole thing just to see that, well, we need that many parameters or not, right? So these are the two possibilities. Yeah, so I think it's time. I mean, before going to the BCI data, the classification, we just run some simulation studies just to see that the method worked well in that case. And we did a lot of, let's say, simulations based on different types of models of point processes, right? For example, here we use the Poisson process as the classical random process, and then we use log Gaussian, Thomas processes, Matern, various gamma process, Cauchy process, but also we use this for the, let's say, for the side of clustering models, but we also used, let's say, regular models or inhibitory models like determinantal point processes, Strauss point process, and air interaction point process. You see a big quantity of different possibilities of different structures, and just to test our let's say our method over all these sort of things. Just to give you an idea of all these processes, the simulations of them or realizations of them are given by this. And you see the difference between them. From Poisson, then you have in the middle the type of cluster processes, and then you have the kind of regular inhibitory point process on let's say on the down part, on the bottom part of the plot, right? And then we compared our well, this is the pair correlation, right? And this is an example of why summary statistics, they don't work in many cases. Why? Because two different models, they share the same pair correlation. Then how can compare two realizations that they come from different processes, but then we use the pair correlation and they are the same. So this is a very clear motivating example that some of the summary statistics, they are not useful at all. Right? Good. Well, so we run the method and we use all these, let's say, setup or let's say network design, right? So we started from images of 128 times 128. This is for our counting data, right? X bar, fine. And then we used 4 different layers. From the first one, third one, and the final, which is the perceptron, right? The first layer, it uses 8 different nodes, remember, which it means 8 different kernels, right? These kernels were dimensions, this dimension you have here, 9 by 9 or 3 by 3, fine. Then we use the regularization parameter, this delta that appears here, and we use a second layer, a third, and the final one. So you see, things become complicated in the sense that with these only 4 layers, at the end, the network parameter, I mean, the dimension of theta is nothing less than 213,000 components that have to be estimated. So this means that we have to be very careful in the architecture that we're using, because we obtain the results like this. And just to give you an idea, for example, you see our CMS network, which in the validation or training, which is kind of the yellow and purple lines, you see the accuracy they are obtaining from starting from, let's say, from almost 90%, and it goes down to 60%. Right? Remember that 10 is the temporal replications in this case, right? So, and this is much more accuracy compared, for example, to the random guessing, which is nothing, basically it's random guessing, or even to the intensity. I mean, if we were using the intensity as for the dissimilarity function, basically the intensity is doing the same kind of thing as the random guessing. You see, which is the green and the kind of orange line, right? So if someone uses the intensity, is doing nothing, basically nothing. And we are proving here, we are showing here that using the CMS, we are obtaining much more accuracy compared to the classical summary statistic, which is the intensity. Right? So this is the overall message of this. And then as the application, we go to the BCI. Well, again, the BCI is, remember that we have a number of, all these number of species with all these hundreds of thousands of point parents there. And the idea is classification in the species we have there, right? So, so the thing is that the network or the architecture we used, again, was based on this, on 4 different layers with the final perceptron in the output, with all these nodes and dimensions and regularization parameters we have here, and we ended up with maybe it's something like 7 million components, which can be a lot, but the procedure can deal with this, and this is the good thing. I mean that we can build these very complex architectures and we end up with these millions of components, but everything seems fine as an output of the classification, right? And this is our result. You see, random guessing again. We compare with random guessing, which means do nothing and just random guess. This is lottery, and basically with this thing we have this red, the green line, and you see, in contrast to that, the CMS network, our proposal is clearly up there. The accuracy is around 100%. So we are providing much more, let's say, accuracy if, for example, we were using the K function as a summary statistic. And a funny thing here, not funny, but interesting thing here is that the intensity has lots of important things here. You see the intensity, which is the orange line, is close. It's a little bit less accuracy of the CMS, but quite close. It's better, for example, than the K function. That's an indication that the intensity, the degree of inhomogeneity is very important in these BCI data. Absolutely important. It provides better results at the K function, but a little bit less good results than the CMS network. Fine. So now let me, the conclusion is basically, if some of you are interested in terms of computation, this is done using the Python library Keras and TensorFlow. The intensity and other summary statistics are calculated using the R package stat. And we have a code available just for you to play a little bit with that and to learn using this existing code. It's here in the GitHub. Now let me go probably quickly because I think I have used most of the time. Yes, I'm posing a problem and giving you the solution, but this is just kind of just for you to let's say to be interested in something which is going on here. And something which is known here is the following. I mean, in statistics, in point process statistics, one classical solution to testing, for example, interaction between space and time is a classical random permutation. You have a space, the locations, you have times, and then you permute them, let's say, randomly, the times. In a sense, when permuting, you are destroying the temporal structure, and in a sense, you are under the null hypothesis of no space-time interaction, right? This is a classical thing. Now, if I come to you and say, this is the same point pattern. The black one is the original Hawkes process, the black points, and the red points are the permutated Hawkes process. They are not the same. They are not the same. We are destroying more than enough. So it means that this kind of classic random permutations, we have to be a little bit careful with them. Because permuting, yes, they are permuting. Probably they are, let's say, they are destroying the space-time interaction, but they are changing the spatial structure of the events, of the original events. So based on this motivation, there is something which is called, and then I'm going directly into the solution, something which is called SOP, which is second-order permutations. Second-order preserving permutations. What it means? It means that do not use random permutations, but permutations that keep the original second-order structure of the point pattern. Right? Well, this is something which is done in two stages. This is the first stage. I'm going quickly through this. I just want to give you the idea, not the details. The details are here, and I will be sharing the slides for you. But the thing is that there are two stages: one first stage and a second stage, which is this one here. And with this SOP, second order preserving permutations, with this we are able to provide permutations that keep the original structure of the point pattern. And this is the right thing to do in case of, let's say, of point pattern testing. Just to give you an idea, and I wanted to, that is the thing. For example, this is a classical Hawkes point process, right? This is the intensity is from here. There are parameters, and the parameters are this one here. But the important thing here is like this thing. top left, the original data. Top right, a random permutation, a classical random permutation. You see, we are destroying things here. Between the left-hand side and right-hand side, we are destroying the idea of the Hawkes process. But then we go to the bottom plot, left bottom. These are three types of realizations of SOP permutations, the ones that we propose. If you compare the different colors, you will see that they are keeping the original structure of the locations. And finally, we compare the L functions. We compare the L function, which is given by the random SOP permutations, which is the green line. You see the green and black are based, while the blue is very different. So random permutations are destroying the original structure of the data compared to the SOP permutations. But not only this, we can do even more. Using a CNN for forecasting, a convolutional neural network. The thing is that with this SOP, we can augment, we can do what is called data augmentation, which means from one realization, we can provide lots of realizations, lots of replications from the original point pattern. And we prove here that using this data augmentation and using SOP for the data augmentation, we provide a much more accurate in our forecasting. Right? So this AUC is area for the let's say area for the curve, which is given by the let's say for the forecasting, right? So it means that the larger is the area, the more accurate you've been in your forecasting. So we are improving our accuracy in forecasting by using SOP for data augmentation. So SOP can be used for data augmentation, and it can be used for training CNNs and for providing better forecasts with the CNNs. Yeah, and more things to think about, but I'm not going into details. The only thing, just and I'm posing this general question. This is open problem, and so I just wanted to motivate you, just for those of you that are really interested in these things, that things can be even more, let's say, far apart from what I've been telling you right now, which is in a Hawkes process that depends on a kernel function in this K. You can do kind of a trick. The kernel can be reparameterized in terms of, you see, it originally depends on T prime T and S prime S, time and space, right? So it can be reparameterized by T prime, and then the difference in T's, right? And the same thing in S prime and the difference in S, which is difference in spatial locations. And this can be approximated by a number of functions. Functions which are basis functions that depend on time on one side and depend on space on the other. And you can use these functions using what is called a fully connected neural network to approximate these basis functions. So again, we use the trick of basis functions. We have an approximation of the basis function using a fully connected neural network, and then we can provide, let's say, a better solution to let's say, to the estimation of what is called the triggering function in a Hawkes process. Anyway, I think I've I've gone through all the topics. The overall message was that these two big branches of science, which is point process on one side, spatial statistics, and the computer-based machine or deep learning, have a deal together. They can come together in solving problems, and this is one trending topic right now. And probably this is lots of let's say of new things coming along, and especially in the idea of spatial-temporal point processes. So thank you very much for your attention.
Thank you, Professor Matthew. It was a fascinating talk. So for Bapak Ibu participants, we want to remind you that the link for attendance is available now. You may want to access the link on Zoom or YouTube chat box. and we will generate the e-certificate based on this list of attendees, and later today, the certificates would be sent by emails along with the presentations slides. So I think we have some time to address some questions. Let's go straight for question 1 from Muhammad Fajar from Statistics Indonesia, BPS. His question is, does the process of transformation from observed point realization to feature space to pooling metrics guarantee that the original information remains intact? Could there be a risk of information loss due to this transformation process?
Yeah, this is a very good question. And in one of the slides that I went through kind of quickly, I showed that there is a Kolmogorov representation of function that guarantees two things. One thing is that this transformation keeps the original structure of the original point pattern. This is one thing. And this is based on a probability, let's say, result from Kolmogorov, right? This is one thing. And this is, for me, that is the, let's say, the right result in terms of probability. And the question is really important, because sometimes, I mean, doing neural network things is like, we really don't know what's happening there inside when all these number of thousands of parameters involved. And I show during my presentation 2 slides. One of is this Kolmogorov representation, and the other one was a slide where I was showing that the probability of these feature maps called H being less than Z, they clearly had to do with the probability distribution of the point pattern itself. So it means that the original probability distribution is there, is providing all the information from in the capital H matrices. So with these 2 results, we are sure that we are keeping with the original structure of the point pattern.
Okay, cool. I think that's clear enough. And second question from Mawanda A. He is joining with us on Zoom, and he's from Universitas Andalas from Sulawesi. So his question is, the result of the feature map depends on the filter. And as far as he knows, the value in the filter can be generated from the random number or from a certain distribution. So what happens, and what should we do if the result is different from the same data set every time we change the value of the filter?
Yeah, again, a very interesting question. Yeah, this is true. The truth is that the filters, this is something that the user or the researcher are, let's say, selecting, right? But because this depends very much on the kernel or on the filter, we have the possibility to use from one, this K that was in the superscript of all our matrices, it went from 1 to L1 in the case of the first layer, or L2 in the case of the second layer. So we have the possibility of using a very large number of kernels, of filters, just to avoid the problem of depending on only one selection of them. So when one has a clear idea of the type of kernel that one should be using, then it's fine. Then use only 1 or 2 different things, and then that's fine. If you are not aware of anything about that, then you can really do a kind of, number of up to L number of different kernels. And in terms of the values of the kernels, I mean, the kernels could be Gaussian kernels, could be different types of kernel. I mean, we have lots of that possibility, right? This is as in classical statistics, that there is one result in non-parametric statistics, non-parametric estimation, kernel-based, which is that the use of the kernel is not that important as, for example, the bandwidth selection, right? So it doesn't matter kernel or you use another type of Panechnikov or some other types of kernel. So here it's the same, that, yeah, you can use all, some of them, but at the end, after all, let's say, the convergence to the output, the use of a particular kernel is not that important. We have the same type of result as in classical non-parametric statistics.
Okay, thank you, Professor Matthew. We still have some time for more questions. Let's see, I have here question number 3. We have 4 more questions from the same person. So the first question from him is that it seems that the idea works fine in the spatial case. So what does the time particularly play a role of here?
Yeah, again, this is very nice spotted. The thing is that in our particular case, t, the time, is considered as a replication, not exactly as temporal dimension. Why? Because in this BCI data, we only have 8 temporal replications. This is not enough for a temporal dimension, right? So what we did was something like, fine, we have the spatial point patterns in T1, which is a first like sampling scheme. Then we went to T2, a second one, that is kind of deep. It depends on the first one, but it's not considered as a temporal dimension, temporal varying the varying dimension. So ideally, this procedure could be extended into a real spatio-temporal point pattern structure. But right now, time, the capital T, is only considered as a replicates of several, let's say, sampling schemes, and not as a space-time thing.
All right, next question. Oh, wow, so many questions. Next question would be, so earlier in your presentation, you said that there is a hidden feature in this point pattern problem. So the one who is asking the question is not really sure if they caught what it meant. Could you please elaborate about what is the hidden feature here? Is it related to the hidden layer in the neural network, or is it something different in how you create the grids in that matrices of the spatial problem?
Well, as I said, one thing is let's say a hidden layer. Another thing is a hidden feature. I mean, when we say feature in point patterns, a feature is a particular characteristic. And we said that the features are coming in the capital G function. And G could be or based on the intensity or based on the summary statistics. So the thing is that the features are particular characteristics of our point pattern. So features could be number of events in particular subregions of our space. Features could be distances between locations, between events. Features could be whatever distances to the nearest neighbor of some other thing. So features are particular characteristics that we can extract from our point pattern. This is the idea of the summary statistics. When we go from summary statistics into neural network, the idea of the neural network is to extract the same kind of thing, but we cannot say that they are distances. We cannot say that they are a kind of a number of events. The only thing we know is that these are, let's say, particular structures that are hidden in our point pattern that we cannot observe, but the neural network is kind of extracting. Right? So, I mean, to be a little bit more clear, the idea of a feature from the neural network is more or less the idea of these features that the different summary statistics are extracting from the data itself. But in any case, they are hidden. I mean, they are hidden layers. This is something we are not observing. we are just counting from the discrete size. When we convolute with the kernel, with the filter, we're obtaining some other thing. But these other things are something inherent in the point parent structure that we are not observing, and that with these operations, we are kind of extracting.
Got it. So Muhammad Fajar, who was asking about the loss of transformation earlier, he got a followed up, comment about the discussion. So he thought that indeed the distance between distributions reflects an indication of information change, but the formulation is needed to translate the distance between empirical and theoretical distributions into entropy. Do you have any comment on that? Into entropy?
Entropy, yeah. Yeah, that is a good question. Entropy, yeah. Probably the one who is formulating the question is working on information theory and entropy-based information. Yeah, this is a very good question. I mean, we know that entropy is a measure of can be used in many, let's say, in many different contexts, but in particular in the question, in the context of that particular question, entropy is a measure to define the difference, to measure, not define, to measure the difference between two distributions. That is completely right. And this is true. I mean, here we didn't use entropy, but as a measure of, rather than using L2 distances between two feature maps, we could be using entropy to measure the difference between two distributions. And this can be done because the idea of the neural network is just use a particular, let's say, distance, L2, entropy base or whatever, just to provide information on the differences, right? On the structural difference of the probability. So entropy, I agree with this question, that could be a good alternative to measure discrepancy between distributions.
Okay, thank you. So last question. This is from YouTube, from Dwi Laksana Abdullah. They asked question about, I want to ask question about dropout method. If we use a dropout for some architecture, is it possible that the dropout change the original input to minimize the overfitting problem?
Yeah, again, this is a very nice question. I mentioned two, let's say, two possibilities, two alternative possibilities to control for the overfitting, right? One was the regularization problem, and the other one was this dropout thing. The idea of the dropout is that we have assumed that we have n times m small cells, and we are not using all of them in our fitting procedure. We're using just a subset of them. Which subset? By random thinning, which means that we are dropping out randomly a number of cells, that they are not entering into the whole, let's say, fitting procedure. So by using randomness in this kind of thinning, in this kind of dropping out cells, we are sure that the, let's say, the overall fitting is not being affected by the number of cells that are being dropped out. Another thing is that this is like in point process thinning, random thinning. No? If we were not using random thinning, we would be in a problem in that sense. But using this random thinning, we are fine in the sense that, yeah, we are dropping out some of them, a subset of them, and with the rest, we go ahead and we are sure that everything is the same.
All right. That was a very nice discussion session. We still got some more questions, but the time is running out, so we need to conclude the session here. And before we end this event, I would like to invite Professor Matthew to receive an appreciation certificate virtually. So here is the certificate. There you go. The printed certificate is here, Professor Matthew. We will be giving that to you later. And thank you again, Professor Matthew. thank you to all participants. Please fill out the form for attendance. The link is now available on the chat box on Zoom and YouTube. The e-certificate will be sent to you by emails later along with the presentation slides. And well, we have come to the end of today's international seminar series of world-class professor-like by Statistics Department at Institut Teknologi 10 November Surabaya. Bapak Ibu participants, if you miss any part or some parts of Professor Matthew's talk or the discussion session, you could watch the recording of this seminar on our YouTube channel, Departemen Statistika ITS. Also, if you need more information about recent news or announcement from Statistics Department ITS, please go ahead and visit our website or our Instagram account at ITS_statistics. So yeah, I'd like to thank Professor Matthew one more time for his enlightening talk and discussion. And again, to all participants, hopefully we can meet again in another international seminar series. Thank you. Have a great day.
Thank you, Prof. Matthew. Thank you.
Thank you, Prof.
Hamzah.
Matthew. Thank you. Thank you, everyone.
Terima kasih.
Terima kasih. Thank you.